All right, hi everybody. So today, as advertised, we're going to be talking about conservation of energy. We've already started talking about it last time in the context of a specific sort of subset of conservation of energy. We talked about the work energy theorem, right? And for that, we introduced the concept of kinetic energy, right? So kinetic energy in general for some object of mass m, right? It's moving at some speed v, 1/2 mv squared, right? Makes sense. It's got units of joules, right? Which is what is that? Kilogram meter squared per second squared, right? Looks good. Bigger with the bigger your velocity, the bigger your energy. Notice that. So one thing to think about here is that this depends on your vantage point, right? If I want to know what the kinetic energy is, suppose I throw this chalk across the room and say, what's the kinetic energy of the chalk? Well, for an observer like you who's sitting still in the room, and you say, all right, well, in a reference frame where I've got the coordinate axis x that way, say, and y that way, that's holding still with respect to the room, you'd say, all right, well, whatever velocity v this thing has as it flies across the room, from that vantage point, you'd say, stick it in there, 1/2 mv squared. But somebody who's observing this, somebody who's on a skateboard going across the room with the chalk would say, it has no kinetic energy from their perspective. So the fact that it depends on v tells you you're going to get different kinetic energy depending on the relative motion of the thing you're talking about and whatever coordinate system you're using, right? So I just, anyway, want to point that out. So where's the work energy theorem? Work energy theorem just says that the change in something's kinetic energy, right, where I'm using my old delta definition, final minus initial, right, is just equal to the net work on that object. So it's the net work that's done on that object, right? That's the change in kinetic energy. So that's conservation of energy, because as we saw, we can often think of work as a potential energy, a kind of energy. And potential meant potentially turned into kinetic energy, as is done here. But there's lots of other kinds of work. You can have, sometimes work can be thought of as potential energy, sometimes not. I talked about this last time. I was going to talk a little more today. What I told you was that if you have a force like gravity, right? So if you have some force like gravity that depends only on position, and in fact gravity is even simpler than that, it doesn't even depend on position, then you can define a potential energy. And by that I mean, another way of saying that is that if you have a conservative force, okay, so you have a conservative force. Another way of saying is that if you have a conservative vector field, so you can think of force that can say, if I write down a little vector, if I put a little arrow everywhere in space, representing how much force, actually it wouldn't be that way for gravity, straight down, right? A little force vector. If I drew a force vector everywhere in space, representing what force this chalk would experience if it were in that location in space, well, it's always pointing straight down. That means that if I do this integral, if I say, well, what is the work on the chalk? Okay, work on chalk as a function of it being moving around, let's say by gravity. Let's do it this way. Lots of subscripts as usual. Gravity on chalk. So this isn't necessarily the net work that's being performed on it, right? I could be holding the chalk, exerting some force on it, in addition to the force that gravity is exerting. But if I take the chalk and move it around the room, I can do that. Calculate the work that's being done by gravity on chalk and say, it goes from some initial position R1. Let's do this. Let's first ask this. So there's a funny symbol in the book for an integral sign. They put a circle in the middle. It just means a closed path. It doesn't tell you it's necessarily going in a circle. This just means it's a closed path. You start and stop at the same place in space. If you ask about the work done by gravity on chalk in a closed path, some closed path, and say, all right, what is the work done? That's easy. That's just the force, right, of gravity, dotted with your little infinitesimal, your little infinitesimal displacement right there, so f.dr, and you go around and you calculate how much work is done. Well, this will always turn out to be 0 if you go on a closed path. The amount of work that gravity does on this chalk will be 0, no matter what path I take, as long as it's a closed path, right? And so last time we talked about a path going up a mountain. I said, well, it doesn't matter what path I take. If I start at the bottom of the mountain someplace and I end up at the top of the mountain, if I go through the careful calculus and trigonometry and get all my angles right and figure all this stuff out, the contribution of the work done by gravity, it's going to be the same no matter what path I take. Well, this is another way of stating that result. So the way the book states it, it just says, any closed path, you're going to do 0 work, right? Because after all, any closed path, the change in the height, right? So the change in potential energy due to gravity, we figured out, right? Is just going to be mg times the change in your height. Well, if the closed path, delta h is going to be 0. This will always be 0. So this is a special case of this general phenomenon, right? Any force that has this property, so that the work is always going to be 0 for any closed path, you can define a potential energy for it. And that's why we were allowed to do that for springs, right? And we calculated that last time. Spring has this property as well, right? If you take some mass, don't even about the mass right now, let's just use my hand. I'll put my hand on the spring and say, okay, if this is the equilibrium position when it's just sitting here and there's nothing hanging on it, and then I pull down some amount, and I go back and forth, do all these different things. Well, if I come back to the place I started, the resulting amount of work that was done by the spring on my hand is 0. Because at every stage, if I move down in this region right here, well, when I came back to that place and I revisited that place again on my path back, they exerted the same force on my hand as last time. It's just this time I'm going the opposite direction than I was the first time, so it cancels out. So this has the same property, that if I took a g out there and put it as sp for spring, if I take a closed path, that's a one-dimensional path going up and down. Right? But any closed path I take, if I wind up back in the same place I started, it's going to give me 0 work. And so the upshot of all that is that when you have potential energy, it allows you to define work in terms of a difference between, it's only a function of the endpoints. That's what I'm trying to say. Only a function of the endpoints. With gravity, it's even simpler. It's only a function of the height difference, right? It doesn't matter even what the x or whatever the horizontal displacement of your car is, the bottom of the mountain versus where the peak of the mountain is. It doesn't matter. All that matters in that case is just the difference in the height. So that's even a more special case because gravity is always pointing straight down. But if you have some vector field of force where maybe the force can change, you can point in different directions at different points in space, as is true for this, like for the spring, right? This guy, the force is pointing up right here, and it's pointing down when I compress the spring. But every time I go to this position, it's always pointing the same way. It's always pointing down. It doesn't matter how fast I moved when I was there, or how long I lingered there, or it doesn't matter what my acceleration was. None of those things. All that matters is the position. Then it has a property that it only depends on the endpoint. Anyway, so I'm only belaboring that, but that's potential energy. So there's other kinds of work though. Like you could be asked about the work done to say I've got some objects like my dresser, and I'm moving my dresser. I'm bored of my room. I want to move my dresser to a new location. So I decide to move it. I drag it across the floor, or push it, and I push it across the floor. So did I have to do non-zero work if there's friction? And I'm excited to tell you there's actually probably there's friction on the floor. There's friction on my floor. So did I have to do non-zero work to push my dresser over? Yeah, I did. Is it positive or negative work? So is it positive or negative work that friction is doing on the dresser? That's right, because the displacement's that way and the force is going that way. Now, if I return it back to where I came from, so I push it that way first, and friction did negative work on the chalk, right? If I push it back, now in that case, was the work done positive or negative due to friction on the chalk? Yeah, it's still negative, right? Because in this case, displacement was that way. I didn't even say which way my positive and negative x-axis is, right? I didn't even do that, but it doesn't matter. For figuring out the sign of the work, it doesn't matter which convention you choose for your axis. So if I push this guy this way, displacement is that way, but the force friction is that way. Opposite direction, you get minus sign, take the dot product. The work was negative on the chalk due to friction. If I go back the other way, both of those things change sign. The displacement's that way, the force of friction is that way, right? So the result is that I did negative work to go that, or excuse me, I did positive work. Friction did negative work on the chalk. I went that way, friction does negative work on the chalk that way, it doesn't cancel out. You just get twice as much negative work, right? This is not the same thing as gravity. That was negative work by gravity. That's positive work by gravity. That's why when I come back to the same place, it cancels out, right? Things don't cancel out though with the friction. With friction, you're always paying, right? If I drag this guy around, I get a Big Mac, get a whole bunch of energy, right? I can expend the energy, right? I push this thing across the floor, right? But then I want to bring it back. I can't bring it back and get that energy back, right? I have to expend the same amount of energy to push it back. How much energy? Well, we can calculate the work I had to do. It's just the force of friction times the distance, right? I calculate the force of friction. So this is kinetic or static friction? It's kinetic friction because this thing is sliding on the ground. That's interesting. So what about static friction? So kinetic friction can do work. In fact, as we just saw, it was negative in both directions. In general, kinetic friction is going to be doing negative work on things that are getting dragged around, right? Or they're being resisted by friction forces, right? That's kinetic friction. But what about static friction? Well, if the table's holding still, like, if in our reference frame, we define our axes, okay, I'm going to have a reference frame right here, x-axis, y-axis, whatever it is, holding still in the room, right? Table's not moving. Well, if the table is exerting static friction, a force of static friction on this chalk, the chalk's not moving either, at least not the part that's touching the ground. Like you saw with the cartwheel and wheels, it's possible to have some parts moving. You have a situation like this, right, where parts are moving. But as long as the part touching the ground isn't moving, that's where the friction force is acting. So let's just do it like this. So in that case, how much work does static friction ever do on anything? It does zero, because work, right, is work in general, right, it's the force divided with displacement. Right, well, this is for constant. I just didn't write it as an integral. I wrote it as a constant force, so that's for constant force. Right. Yeah. So if that's true, then yeah, you never have delta R if things are static. So static friction doesn't do work. There's a caveat there, though. If you observe, and this maybe it's more complicated than it needs to be, but just to be pedantically, to tell you the truth, I want to tell you the truth. If the chalk right here is, if I'm pushing on one side of the chalk, and so that means it's not moving, then okay, that means that there's some, it's very small force exerting, there's not a friction here. But if I'm exerting some force in the chalk, it's not accelerating right in this room, so okay, it must be that the table's exerting frictional force that way, but it's doing a work that's not, there's no displacement. So over some period of time, the work is done. If you observe this from a car, if you drive by and watch, well, it is moving in that case. So in fact, static friction could do work if the reference frame you're viewing it from, has both the table and the chalk moving. So, okay, in that case, work's being done. But 99% of the time in the class, what you're going to be confronted with is a situation where there's some static surface, like a table or ramp, the road for a car problem, whatever it is, and something that's on it, whether it's a tire or something standing or a block or whatever it is. And if it's static friction, then the thing's not moving with respect to the ground, and in a reference frame that's holding still with respect to the ground, there's no work. So that's just a good thing to keep in mind, that there's no work being done by static friction in those unless the two things are moving, okay, but otherwise, there's no work done. Whereas with kinetic friction, the work is going to be negative, and it's not conservative force, right? So you have to think about it separately. So I'm really making a big distinction between these things we can think of as potential energies and stuff we can think about in terms of work, because when we get into conservation of energy, we'll be able to have a bunch of energy terms from springs and gravity, right? But we're not going to have them for friction, so we have to include that as a separate piece. All right, let me ask you this. So energy's conserved, right? But if I do this, if I do some work on the chalk, well, it wasn't moving at the start, it's not moving at the end, so the change in the kinetic energy is zero, right? Well, where did the energy go? So friction did negative work on the chalk. Let me ask you this, though. I did positive work. I was pushing. Where did the energy go? It didn't go into the kinetic energy of the chalk. I exerted the force for a while. Like there's delta x, right? There's force. No kinetic energy. I was cheated. So where did the energy go? Yeah, so you're saying it went into friction, but friction isn't energy. Like, where did it go? What's different about the situation now than before? I'm sorry. That's interesting. That's actually true. Sorry? Heat into the environment. Right. So part of it was lost in the form of heat. And you know this, right? My hands are warmer than they were. Why? Well, because I took that Big Mac I ate, right? And I did this, right? I put all this energy, and I lost the chemical energy, and so where did it go? Well, this frictional force, right, that was being exerted resulted in thermal energy. So, and we're going to do that later in the semester. So yes, if I heat my hands up this way, all the energy's still there, but it's in a different form. In fact, it's no longer in the form of potential energy. So my hands are warmed up now, and I can get some of that energy back, but not all of it, as we'll see later in the semester, to do useful work. If you have potential energy, you can convert all of it to useful work. You can convert all of it into changing the kinetic energy of the chalk, say. Right? But if you just have your hands warmed up, if you have a hot bath, heat bath, you can get some of the energy out to give kinetic energy to the chalk, but not all. So we don't call that potential energy. It's not as good a form of energy. In fact, why is there an energy crisis? Right? Why do we bother to drill in the ground and get oil in the first place? If energy is conserved, why do we ever run out of it? Right? Why is that? Does anyone have a scattered answer to that? Like, why bother to keep getting new sources of energy if energy is conserved? Can we use the energy? So if I put gas in my car, I drive my car around, the energy ultimately goes where? Yeah, to heat the environment. It's there. The energy's still there. We can count the calories, or we can count up how many joules of heat, how much joules of energy are in the air. But it's not useful. It can't be turned in a convenient way. Or not convenient. It can't be converted in any way fully back into the kind of energy that you could use to move your car someplace, to do something useful. So that's the thing. Oil actually provides, right, and other things do too. But oil, for example, provide the kind of energy that you can control it, you can use it. All right. So anyway, very good. So there's a bunch of topics. So now, how do we use this stuff? Well, what I would do, I'm sort of fancy about the way I write this stuff out. I'm going to write all my conservation of energy equations this way. I'll say, let's write down. So this is conservation of energy, that's what I'm using right now to solve some problem, right? And say, okay, whenever I do this, I'm going to write down a list of all the energies in the final state of the problem, subtract all the energies in the initial state of the problem. So this is going to include kinetic energy. And I have to be really careful what's inside these parentheses, what I'm referring to. I'm referring to some system. The system might consist of a single object like this chalk, but it might be me and the chalk. Maybe me and the chalk and the table, or it depends on what you want the system to be. It's just like all that stuff we did before when we were thinking about F equals ma, Newton's second law. We had to think about what is the system, right? To figure out what forces are to be included in that equation. Same thing for conservation of energy. We have to think about what the system is. So for some system, we'll write down the kinetic energy. And if it consists of one object, it's just the kinetic energy of this one object, right? If there's two objects, we have to sum them both up. What else do we have? Well, we might have potential energy due to gravity, right? We may have potential energy due to a spring. Maybe there's a spring in the problem. Maybe there's three springs in the problem. In that case, you have three terms over here. So it's all the energies in the problem for that system, whatever your system consists of. And there may be more stuff. There stuff. But these are the ones that tend to show up a lot in this class. Potential energy due to a spring, potential energy due to gravity, kinetic energy. Kinetic energy is always going to be. It might be zero, but that's one thing you have to always consider. What is the kinetic energy? It'll turn out different kinds of kinetic energy later in the semester. In a couple of weeks, we're going to have rotational kinetic energy as well as translational. But right now, we'll just think about translational. Okay, so that's the final state of the system. Now we subtract the same thing from the initial state, right? Kinetic energy, potential energy, gravity, potential energy, spring, right? And you do your accounting. What is the statement? The heart of a physicist is an accountant, right? Sit here and count all this stuff up. What does this equal? Well, if energy is conserved, then it should be equal to 0, right? But we'll sometimes have a non-zero thing over here, and that's if we don't have a closed system. If it's not a closed system, then you have to worry about the external. This is net work from external forces. That's what EXT, I mean external. What do I mean by that? I mean that if my system consists of the chalk and me, and maybe I'm pushing on the chalk, well, that doesn't show up here. That's not external, right? That's an internal force between the system that consists of me and the chalk. If the system I'm talking about is just the chalk, then me pushing on the chalk, well, that's an external force. I could do work on the system. I could change its kinetic energy. If you can imagine if I had a chalk right here, and I shot put it straight forward, right? So the reason I say shot put, I'm not trying to throw it. I want to go that way. So its height's not changing. Well, the potential energy, the gravity's not changing. There's no spring in the problem. There's just kinetic energy final, kinetic energy initial. But that can actually be non-zero, right? Or there can be a non-zero change. It's zero kinetic energy, absolute kinetic energy when I'm done. Why is that? Because I exerted a force on the system. So that would have to show up here as a work that I exerted through that external force. So I've got to include that term. Now it's important if I have work here. This is the work done on my system. So I'll say network, on system, right? As always, the subscripts on system, by the external forces, right? So this is the work done on the system. That's why I've got final minus initial, right? Otherwise I go the other way around. Okay, great. So we're going to use that general construct over and over again in lots of cases, and it's going to make our life a lot simpler than what we would have had to do if we were doing Newton's second law. So here's the example we talked about briefly at the end of last lecture. My amusement park, got my roller coaster, and you can see, right? It's a real benefit because suppose what we wanted to do is calculate. Suppose the question we're asked, and that's another thing. Conservation of energy is really useful for some questions, but not for others. It's really useful if the question is, how fast is something moving? Right? If all you need to know is the speed of something, well, that's great because kinetic energy goes like v squared. So that means as long as we know what the initial velocity was, and we know these other energy things, and we know what work is done, well, then we can figure out what the final velocity is. And notice that because these things are easy to deal with, potential energies they only depend on changes in height for energy, gravity, and changes in your displacement from the equilibrium position for a spring. These are really simple things to work with, much simpler than trying to solve Newton's second law at every stage of the way along some crazy path, this curvy path where the acceleration is changing. In fact, the acceleration vector, the direction of the acceleration is changing when it goes through the loop. Remember we did the thing with the water bucket where I was swinging that around? In that case, I was trying to maintain a constant speed for the water bucket. But this thing's not constant, right? The acceleration, as the guy goes around a circle here, the acceleration, when the ball's going up this way, it's not pointing directly at the center even, right? In fact, is it a little bit above the center or a little below the center? The ball's coming up like that. So where's the acceleration vector point? Directly at the center, below the center, or above the center? Who thinks above the center? A couple hands. Who thinks below the center? A few more hands. Who thinks directly at the center? Wow, okay, so that's worth talking that through. So answer this. Is it speeding up, slowing down, or not changing its speed right here? The first time. Is it speeding up or slowing down right here? Slowing down. So that means that there's a component of the acceleration that points what? Up or down the slope? Down the slope. And you know that because gravity points straight down. If this thing weren't slowing down, if you were moving at a constant speed, his acceleration vector would be pointing directly at the center of the circle. But he's slowing down. So that means that gravity's working on this thing too, right? Not just the normal force. So if it were just a normal force, right, pointing at because normal force points directly at the center, it's perpendicular to the track. If it were just a normal, if we were in outer space doing this, right? Then what would happen is this guy would be accelerating directly towards the center. His speed wouldn't change. He'd just run around in a circle at constant speed, right? But because there's gravity, that means there's a downward force of gravity acting as well as the normal force. The resulting force vector doesn't point directly towards it's down like that. Therefore, by Newton's second law, the resulting acceleration isn't directly towards the center. It's also a little below. It's pointing at a point that's below the center of the circle. It's down here somewhere. What about over here when it's going downhill? Is it speeding up or slowing down? Speeding up. Is the acceleration vector pointing directly at the center, above or below? It's below. Now some students are irritated by this. They'll say, well, what, over here, it was going uphill, and you said the acceleration vector was below the center. Whereas over here, it's going downhill, and now it's still below the center. That's true. That's right. So the acceleration doesn't necessarily have to line up with the direction of motion, right? It's just like when I throw the ball in the air and say, well, which way is gravity? Which way is the force of gravity on the ball? When it's in the air, on the way up, gravity points down, the force of gravity, right? On the way down, it still points down. Doesn't matter which way it's going. The same thing's true here. But anyway, all right. So very good. I have this guy do his loop-to-loop. We could calculate the direction of the acceleration vector, and everywhere along here using Newton's second law. What a pain in the neck. So instead, we're going to use conservation of energy. And here's the problem. Let's say that I'm told, okay, I've got some roller coaster like this, right? There's a loop, and off it goes. Let's say that it starts off over here someplace, and this is some height h above the ground. So I'm starting off some height. So what are we given? We're given h, the height, right? We're given the mass of the roller coaster. Here's a little roller coaster. Here he is, his little wheels, right? And he does this. And we're asked to find the final velocity. And here's the final velocity. He's right over here someplace. Some random location along here. And let's go ahead and specify it this way just to be specific. Okay, all right. I should make this. I'm sorry if I do that too small. It's a theta, that angle from the horizontal for no good reason, just because I choose to represent it that way. Let's say that the radius of this circle is r, right? Okay, great. So there's my situation. So how do I use conservation of energy? What I do is I write down this thing and I plug all the terms in. Oh, and what's initial and final? Here's my initial situation. And let's say we're told something else. We're told, we need to know one more thing, which is what the initial velocity was. Let's say that we're told that the initial velocity is 0. The initial speed here is 0. Okay? And let's say that this is position A. Let's say this is position B. We're going from point A to point B. All we want to know is what's the final velocity. Excuse me. Let's say let's do final speed. Actually, though, there's no difference, right? We can calculate the velocity if we know the speed, because we know what direction it's moving because of the shape of the track. We can figure out what the direction of the velocity is, beginning its length, in the magnitude of the velocity.